Okay, so today it's a great pleasure to have Carsten Dominik from the University of Amsterdam here in Heidelberg to give a colloquium. And so let me briefly tell a little bit about his vitae. He made his PhD in 1992, I believe, in Berlin on the topic of dusty HEB winds. He made theoretical models of how dust was formed in HEB winds and how they drive these winds via the radiation pressure. Then he moves to NASA Ames, the United States, to work in sunny California with Alexander Thielens on the topic of dust coagulation. So the question of how dust particles move and then eventually hit and then stick and become ever larger aggregates. And the work that he did then and has been doing since has formed really the basis of a whole industry of dust coagulation modeling. So I think all the people who do dust coagulation modeling in protoplanetary disk and other environments, they all refer to the Dominik and Thielens paper, and of course also a lot of work since then. So this is a very seminal work. Maybe a lot of people know also that I work a little bit in this field, and I have to admit that I essentially learned everything from Carsten, so I'm very thankful for that. After that, Carsten moved back to Europe. He went to Leiden to a postdoc in Leiden, and then moved on for a senior scientist position in Amsterdam. And right now he is a full professor and chair of the group on planet formation in University of Amsterdam, and he's also an honorary professor in Nijmegen, University of Nijmegen. And so today he's going to talk about transition disks, I believe. Yes. And so I would say let's welcome Carsten to Heidelberg and let's hear his talk.
Well, thank you. Okay. Thank you very much, Case, for your nice introduction. It's really fantastic to be here. Heidelberg feels completely like home for me because I've been here so often, and I have so many great collaborations with people at this institute. So it's a great pleasure to be here and to tell you some of the work which we have done in the recent years on the field of Herbig stars. I would like to talk to you about Herbig stars and what we have learned from them and why we think that they are really great targets to think about planet-forming systems. Of course, this is not work which I do by myself, but there's a lot of collaborators. I think actually I should have put Thomas Hellig also on this. I forgot. Okay, many people are very important for us. It's mostly, of course, PhD students. There was a conference on Herbig stars in Chile a week or two ago, where I unfortunately couldn't go. It was done because Herbig introduced in 1960 the Herbig stars, which is a group of intermediate mass young stars. So it's it's often being thought of as that these are the counterparts to T Tauri stars. They are of spectral type A or B, and they have infrared access, they have H alpha emission, and they were associated with reflection nebulosities. This was at least the definition which George Herbig used at that time. We now no longer care so much about the reflection nebulosity. In fact, we prefer Herbig stars without reflection nebulosity because they actually make much nicer targets for disk observations. So there's a group of so-called isolated Herbig stars which are not really so close to molecular clouds that can be studied really well. Yes, and the reason why we in Amsterdam have been focusing very strongly on these stars in order to study protoplanetary disks and planet formation is that they are really an amazing group of targets. So there's a list of a couple of 10 young stars like this. They are at distances of typically 100 parsecs, so that's similar to the T Tauri stars, which most people look at in order to study star formation. But of course they are much brighter because they are heavier stars, much brighter. And it's also so that if you look for a location in the disk with a specific density, temperature, for example, if you look at a snow line or so, that is further away from the star because the star is more luminous, which makes it bigger on the sky, so that means that imaging of these disks really has a lot of great advantages. And we think that these stars have been really pivotal in all these studies. Very often discoveries were first made in the Herbig stars and then later followed up in the Tauri stars. So let's start by looking at a few things of evidence for planets, because many of the early planet searches, which relied on radial velocity observations, were focused on main sequence stars and then more on G-type and K-type, of course, because they have so many lines, so we can do the radial velocity observations. But now it is actually the case that there are more and more planets discovered about Herbig stars, so that also justifies to use these objects as objects to study planet formation. So of course this is the famous image of Beta Pictoris B by Lagrange et al. In 2008. I think it was an L-band image where this planet was discovered and then it disappeared behind the star, and then in the meantime it has come back on the other side of the star. So that's one of the imaging works. That's also one of these things where if the systems around these A and B stars are a little bit bigger and more massive, you can also expect maybe heavier planets further out, which also makes them easily discovered. This, of course, is HR 8799, very famous image. Here's another picture of Beta Pig by Lagrange et al., where you see these planets, which are massive young planets and which can be discovered in images relatively easily. This is a plot from the exoplanet database, where you see detected planets as a function of host star mass, and indeed, so you see now that the studies really are eating into this direction of 2 solar masses, 3 solar masses, and really getting nicely into this regime. Of course, there are still many fewer discoveries. In particular, there's many fewer planets at lower mass, and that again has to do with the fact that these heavier stars have fewer lines, so the radial velocity studies don't really work so well. And also, of course, that the star itself is a little bit more massive, so that makes it also harder to discover planets. But we are getting there. There's a whole population of planets popping up in these systems. What is interesting is that the distribution of planets around these A stars seems to be different. So there's a very nice paper which I recommend to you by Bauer et al. In 2010, which tries to consolidate the observations of massive planets around A stars with earlier derived formulas for the frequency of planets around solar type stars. So basically the simplest way how you can do this is that you just try to fit the planet distribution with a power law for the mass and a power law for the period in a logarithmic space. And then there's an older paper by Cumming et al., for example, which gives values for these parameters. So they found that alpha is minus 0.31 and beta is 0.62. And they try to use the observations of planets around A stars and consolidate them. And so they do a very detailed analysis and show that, for example, these low values of alpha, even negative values of alpha, can be very well excluded for these heavier stars. So there's a different power law for the distribution as a function of mass, which is interesting. So that means that the fact of how the system looks like and what the properties of the star are do matter for the planet formation process. That is a hopeful sign, because if you want to understand planet formation in the end, it's good to have systems where things work in different ways and they produce different kinds of outcomes. Today in the theory meeting we had a nice talk about population synthesis. I think this is exactly what people who try to do population synthesis want, that they have different systems which do different things, and then you can try to learn about the processes which are behind planet formation. It turns actually out that the planets in wide separation are relatively rare. So it turns out that, for example, from the, I think that is the Niki survey to try to find planets, and that was not really so successful, not finding many planets at large distances. So these cases which we have, which is HR 8799, for example, they appear to be relatively rare. So there's not a big number of these planets out there. It turns out that planets actually form further on the inside. And one of the amazing results in the recent year was that there seem to be now a couple of candidates, at least for protoplanets, which are still embedded in the disk. This is a paper by Sasha Quantz, which looks at the famous Herbig star HD 100546. I'm going to talk more about this star, which is probably the best studied of these Herbig stars, which has been looked at by basically every telescope which we have. And so this is an image taken there with a special faceplate, and there's a location here in the disk where there's a little blob which they interpreted as being an exoplanet candidate in this system. And I know that this is not the only candidate that there is right now, so I think there's going to be more observations coming out soon showing similar results. And of course, this is also fantastic that we now start to see disks where planets are still embedded in the disk, which is going to be fantastic when we try to think about migration theories and stuff like this. If we look at the Herbig stars, so where they fall into this entire picture of planet-forming disks, one interesting thing is to realize is that they are actually disks which are relatively far evolved. And one way to visualize this is looking at evolutionary tracks in the HR diagram and seeing that where these stars are located, these Herbig stars are, most of them are actually relatively close to the zero-age main sequence. And in particular, if you compare this with objects which are still embedded in pretty young clusters, so there's a couple of clusters which were studied by Arjan Wick and Koen Maaskant, which have ages of 1 to 4 megayears of clusters or so. There's a lot of embedded objects still in there. And then all these isolated Herbig stars, which we have been looking at now for 20 years, are actually really clearly removed from this group and are very well on their way to the main sequence or already very close to it. So that means that these objects may very well not be objects which are typically of a young disk, but they are actually already quite evolved objects. You see this already in these HR diagrams. This is just how the time decay with a frequency for accretion or for dust decay. So typically, the time on which disks disappear is something like 3 million years. There's a couple of observations which shows this now. One of our entries in Amsterdam into this field was the paper by Gwendoline Meus in 2008, where we looked at the spectral energy distributions of these stars and decided to put them into groups. I mean, that's what you always do. Eh? As a stem collector, you first look at the stems which you have and you try to put them into groups. And there were 2 basic types which we could identify. And we called them group 1 and group 2. The group 2 sources are sources which basically can be described by more or less a power law spectrum over the entire range from basically the moment when this SED turns off from the photosphere all the way down. And then there are these other groups which we call the group 1 sources, which have, in particular in the mid to far infrared, mid-infrared basically, have a significant excess. That's also called group 1. Herbig Ae is an example for such a source, and for the group 2 sources I've put here HG 144432. And so there's a couple of features. So these stars have emission features, silicate emission features. 10 and 20 micron are usually pretty prominent. Then there is a near-infrared excess. There's some excess emission in the near-infrared, which must be due to material which is relatively close to the star because it's warm. Then there is this, at least in the group 1 sources, there is this additional very strong excess in the mid-infrared. Then if you look at really long wavelengths, then actually they are not really different so much, so it appears that the masses of these objects are in fact slightly different, but not so different. Yeah? So then the idea was that the difference between these 2 SED types has to do with geometry of the disk, and the interpretation which we were using at the time and which we then developed further. This was a collaboration between Case and myself, where we worked on this a lot, trying to develop 2D radiative transfer models which can explain these disks, is that you have, so the idea is that you have two basic geometries. One is a flaring disk. So we always have this inner disk which is close to the star, and then a flaring disk which is flaring on the way out, exposing a lot of surface here to the radiation of the star. And the other SED type was a disk which was more flattened, so not exposing so much surface to the star, and that's why there's less excess at mid-infrared wavelengths. Case that I call this self-shadowed, because the inner regions can be puffed up a little bit in this disk, and then they can cast a shadow which would be able to cover a large fraction of this disk. And so the idea for the evolution which came up back then was to say, well, it's pretty clear, so must be a young disk which is full of small grains, and then these grains slowly start to grow and start to settle, and eventually they disappear in the shadow of this inner disk, and then they look like this. So this the evolutionary sequence would be going from here to there. And we have actually been working with this hypothesis for many years, trying to find correlations with large particles and all kinds of things. Well, the next step, what happened is that in the early 2000s, it turned out that some of these disks actually had gaps, which of course everybody expected. If this is really forming planets, at some point there should be planets which are heavy enough to start to carve gaps. So, for example, there was a paper by Jeroen Bouwman, who I think is also in the room, looking at the spectral energy distribution of HG 100546, showing that there should be a gap. There was an observation by Carol Grady showing a similar result. William Benesti in 2010 used interferometric results to also show exactly the same thing, that there's something like a 10 AU gap in HG 100546. Well, then other imaging data, for example, also by Carol Grady in 2009 for SAO 206, and then a couple of extra numbers, which I always keep forgetting. And that's like Quant's imaging data with NACO, and a couple of other people also from the Zurich group who has been doing some good work in recent years. Mitsuhiko Honda in 2010 showed that the extendedness of the 24 micron image for AB Auriga could be explained by having a region in the inner 80 AU which is depleted, which has a depleted surface density. So this starts to look like a pattern, and we have had a student in Amsterdam, Koen Maaskant, who really has been pushing at this, and his main tool were also 24 micron images. So the idea is that you try to look at the size of an object in a 24 micron image, you compare it with a point source, and you see that all these sources are extended at 24 microns, and then you try to model it, and what he came up with is that basically for all these disks which are detected to be extended, the only way to get the extendedness of the 24 micron emission is really by having gaps of increasing size. So if you have a continuous disk, then the 24 micron emission is dominated by material which is so close to the star that you should not be really able to resolve it. We resolve all these disks, so the only way is to take away the warm material which is close to the star. That was basically his conclusion. So this is a couple of the sources which he looked at, and then the cartoon of what his disk structure looked like. So there's interesting, all these disks have some warm material close to the star still, but then there's a region which is largely depleted of at least dusty material, and the size of this gap is different. So it can be 17 AU, 23, 30, or go all the way to 80 AU, depending on which source you are looking at. The other interesting thing which this picture solves is also that back when we created the definition of these groups, so the group 1 actually was split into two groups, group 1A and 1B, and the difference was that the 1A particles had a strong 10 and 20 micron feature, while the 1Bs actually did not have a 10 micron feature of silicate at all. They had maybe pi emission at a similar location, but they did not really have the silicate emission. And it was always a puzzle, so the idea was, are these big grains in there? Well, in this picture with the gap, the natural explanation is just, well, the gap has gotten so big that all the material which is warm enough to really contribute to the silicate feature emission is just gone. And so now, something really funny has happened, because our evolutionary sequence has just flipped. Because now it seems like that these group 2 sources might be the more primitive source. And that then planets start opening a gap, and for some reason or another, are able to also influence the outer disk that it becomes thicker. It's, I mean, Kuhn Maaskanter, our PhD student, says, well, he actually thinks that maybe there's a common ancestor for both of these. But I like to simplify the picture, and I would like to think about the idea of maybe we start from these disks and then move up like this. The next thing I want to talk about is using mineralogical tools to say something about the structure of these disks and the gap. So phosphorite, I'm sure you have probably all that talks about it, because there's people here in this institute which also have heavily worked on this. Phosphorite is a mineral. It's a mineral which is made of is a magnesium silicate, and it actually consists in a couple of forms which can contain some iron, but they can also be completely iron-free, and then it's called phosphorite. It's a crystal which contains no iron. We loosely use this term also for materials which contain a little bit of iron. There were a lot of great measurements for the optical properties being done in the Jena laboratory already 10 and 15 years ago. This is what the features look like. So there's in the 10 micron region there's a couple of features, but then also here at 23 and 34 there's very prominent features which you expect if you have this mineral present. It is interesting because it's a crystal, so that means you need to heat the material quite a bit in order to be able to produce this feature. There's also a very small feature at 69 micron, which looks on this plot really like a completely boring and small. But in fact, it's a very interesting feature because it strongly reacts to properties of these glass planes. So it reacts to the temperature. This is the sequence of different temperatures. So if you have this material at 50 K, you expect a narrow and strong feature. If you have this feature at 295 K or 300 K, you expect that it's going to be broader and it's going to be redshifted. And there's also an effect that if you add iron to this material a little bit, just a percent or 2% or 3%, that also leads to a redshift of this feature. Which makes it an interesting tool to try to look at study the structure of this. So there was a bigger program, the DIGIT key program with Herschel, where a couple of us were involved, looking at the 69 micron feature in particular. And the first paper which summarized this data was by Bernhard Sturm here from the Max Planck Institute, which looked at the different 69 micron features which you find and which you see if you look closely that they do peak at different wavelengths. Here, for example, is a feature which peaks closely to 69. Here's another one, which maybe Riga is maybe not the best example. But it can be different widths, and the peak position shifts slightly. And you can try to use this to interpret these features. So what we have done is we looked at one star in particular, which is HD 100546, again, of course, whichever star could it be. And Gijs Molders, a PhD student of mine, has made a very detailed radiative transfer model, which we published, and he noticed and put emphasis in his paper on the fact that optical depth effects are actually really important for interpreting these features. And that has to do with the following effect. So this is a plot of the disk. This is the height over the normalized height over the disk, Z over R, and this is the distance from the star. This is 10 AU. This is, so the gap here goes to 13 AU. This is at 100 AU. And so what he has plotted here in color are the temperatures. So there's maybe, so this is a 200 Kelvin, and 250 is somewhere here close to 150, 100 Kelvin. So these are these temperatures. And then if you look at the optical depths, you find that if you look in the visual, so in the optical, you see that this disk is actually optically thin to pretty high heights. But if you start looking at 24 microns or at 33 microns, so for these phosphorite features which are located there, you start looking deeper into the disk, and at 69 microns, you actually look through the entire disk. You can see all the dust at 69 microns in this plot. And so we try to do a couple of different tests of how to distribute the phosphorite in the disk. So we try to do a continuous low abundance distribution, or more focus to the rim, was still more focus, still more focus. And one model basically had the phosphorite only at the inner rim and then a little bit on the surface areas, so basically everywhere where the temperatures are high. And he tried to get to a fit of it, and he wanted to fit both all the shorter wavelength features and the 69 at the same time. And if you look carefully, of course, then you see that there's two models which do a reasonably good fit with both the feature ratios and the shape of the 69 micron features. And both of these models indicate that the phosphorite is actually localized in close vicinity of the inner ring. So if there is a planet which is covering the gap, the planet is somewhere inside of the ring, and only relatively nearby you have this crystalline material, which is suggestive that maybe this planet has something to do in one way or another with the presence of this material. Okay. Let's try another star. This is HD 142527. It's a very famous star. It has a gigantic gap. Yeah, 120 AU, basically a big gap where there's very little material. This is a paper from Herbig Ae, very recent, where he tried to really see the material which is in this gap, and he couldn't find it. So there are pretty strong limits, which I don't know off the top of my head, but there are strong limits. There's also a planet candidate which has been discovered in here, so there's probably a planet. There's also beautiful other observations. And there's images at different wavelengths which all show this gap-like structure, where there's this big ring of material in the middle, there's very dense. So like the typical structures which I've shown before, but maybe in an extreme case here, that this gap is really very big in this case. So maybe there are really relatively massive companions or a whole system of planets in this gap. That is one of also possible explanations. The model which we designed in order to try to fit the observations of the star was done by Arjan Verhoef, and there's a new iteration now by Michiel Min, which we are working on right now, that basically has this outer disk starting at 120 or 130 AU, which has a very high scale height, so it really looks like a big wall there, which is actually also what these images look like if you try to interpret them in a geometrical way. Then there's a big gap, and we need some warm material close to the star, and what we had to come up with in order to satisfy both the LCD and also the interferometric observations which test this material is that we need an optically thin component, which in this model was a halo. We are really unhappy with the idea of a halo because we don't really know how to make one. But something like this is required by the observations. There's also an optically thick disk in here, but a very small and tiny one. You could also put all this material into an optically thick disk here, and then maybe still get some emission at the infrared, but there's other problems because this disk would then become so thick that it casts a shadow, which causes problems with the scale height of this outer disk, and so the model really gets worse if you try to do this. So we really like to have an optically thin component here. This is a fit. I mean, it's on a logarithmic plot, so it doesn't really look so good, but it really does a pretty nice job in doing all the features right. In particular, there's a very strong ice feature in the source, which was already seen with ISO, and then it also gives a nice fit to all the new Herschel data which we have here. It does fit the visibilities. So here at 8 microns, the atmosphere becomes very difficult, so I wouldn't really worry too much about this discrepancy here. But in this region where we look with MIDI, we can fit the visibilities very nicely. We can fit the shape and also the degree of polarization, which is seen in this ring model. So this is again the observation by Herbig Ae, and this is here this model. Unfortunately, it's a different color scale, but you just have to believe me that the degrees of polarization are also the same. So this is really a good fit. This is a plot of the ice feature there, which has a peak position at 43.4 micron. And that is interesting. So it's a very sharp feature with a peak at this position, and that means something for the origin and the kind of ice which you see there. So this is from Cummings et al. Measured ice features. They have done 3 series. So this one is they take a plate and deposit ice on it at a given temperature. So for example, if they deposit the ice at 120 Kelvin, they get the sharp feature. If they deposit it at much lower temperature, they get a much broader feature. This is amorphous ice, this is crystalline ice. You can also deposit the ice at 10 Kelvin and then warm it up. And then, of course, it stays amorphous, but then when you warm it up to 120 or 130 Kelvin or 140, then it becomes crystalline, as you would expect. You can, of course, also try to first deposit it at high temperatures and cool it down, and then again, sort of happens what you expect. The feature starts crystalline, and then it remains crystalline. So by just cooling it down, you don't make it amorphous. And then you can try to fit the peak position which you have, and it actually turns out that we have mostly this feature. So this is what the feature looks like, which we have at 80 Kelvin, which is a very nice fit because the inner rim has a temperature of 80 Kelvin, and also the peak position is right, it's in this 43.4 regime. So that means this ice is now at 80 Kelvin, but it must have formed at higher temperatures. So again, this is a similar case that we have a material which must have formed at higher temperatures. It is located at the inner edge of this outer disk, so at the outside of the gap. And so it's very well possible that the possible companion, which is located in this, has something to do with the formation of this material. We don't really know exactly how, but it's a pretty strong indication. What is very interesting in this source is also that these are observations from Mitsuhiko Honda. They basically took images of this disk in different wavelengths in the near infrared and showed that there's an absorption feature of ice on this disk visible. So there's a little bit less flux at 3 micron than there is at 2 and at 4. That's basically his observation. And we do get this feature and reflection also for the model which we have, which is interesting because it means that these ice grains are actually at the surface. So they're at the reflecting surface. There are grains which have an ice layer on top of them. So photo desorption has not completely stripped these icy grains. We started at 5. Huh? So here's another model which we here tried, because I said we hate the halos. So what else can you do? So we tried a different one. We just tried, well, can I also put in a wedge-shaped optically thin component? That also works actually. So that also gives us a decent fit. And one of the things which we have done is to try to think about, well, could you make something like this? I mean, could you make an optically thin distribution in a transitional disk which is poor in dust and probably also poor in gas, maybe not free of gas, but poor in gas? Is there a way to make a structure like this? And this is some stuff which I worked on together with another PhD student, who actually was a master's student, Sebastian Keit. I'm sorry, this is, first I have to say this. We hope that we can decide this question pretty soon, because if there is this small disk which is a little bit optically thick, then you should see this shadow. And this is a prediction for the sphere instrument, for the simple polarimeter, that we think we should be able to resolve this shadow band on the inner rim of the disk with this instrument, if we are lucky. If the optically thick disk doesn't exist, if it's an optically thin component, then it should look more like this. So we hope that we can decide this question in about a year from now. So I said we were trying to think about how could you make something like this. Huh? And when we started to think about it, I remembered from my early classes in the solar system that there was this problem with Pluto's orbit. That Pluto is so strange because Pluto has a high inclination. It's really different. And the explanation for how this works is that Neptune migrated out in the formation of the solar system and dragged Pluto with it in a resonance, and in this way gave it high eccentricity and high inclination. And so that started us thinking if you can come up with a similar way to do something like this. So for Pluto it works like this. Neptune is located at some position, it moves outwards. The 3-to-2 resonance also moves outward, at some point catches Pluto, drags it along, and the eccentricity goes up and the inclination goes up. This is the basic mechanism how this works. And so we tried to do this for an inner disk. So this is not a model where we really self-consistently compute migration, but what we do in this experiment is we look at the inner disk somehow. We put a planet in there of a variable mass, and then we put a couple of planetesimals in there, and we just let this planet migrate in by some mechanism. So this could still be in a phase where we have a relatively decent amount of gas which can push the planet. Maybe it's also in a later phase where the planet is in part pushed by scattering of planetesimals. We didn't really care so much about it. We just wanted to see, can we make something which is thick? So what we did here, we let this planet first migrate relatively fast through this cloud. So what happens is that planet gets closer, it moves through the thing. Actually, indeed, a few of these objects climb up a little bit, are being scattered by this object. So there's a few close encounters, they are being scattered a little bit. So you see that the eccentricity actually goes up a little bit after the planet has moved through. The eccentricities of these objects is now 0.1, 0.2. But the inclination of all these objects still remains relatively low. So this is not a process in order to make a vertically extended distribution of objects. Doesn't work. So then we thought, well, if we migrate a little bit more slowly, then maybe that planet can actually capture the object in the resonance and really drag it up in the resonance, so drag up some eccentricity, and indeed that works, so we get a very high eccentricity. But again, also this process, the inclination still remains very limited. Yeah? So this resonant interaction mainly works on the eccentricity in this case and not on the inclination. But then what we notice is what can happen is that you have the planet moving in. At some point it catches the planetesimal, puts it on an eccentric orbit, on a very eccentric orbit, and then if you then follow up with a close encounter, then the close encounter can get into high inclinations. So that's very interesting. So if you have a scattering event with the planet, and both the planet and the planetesimal are on low eccentricity orbits, then you don't get high inclinations, but if you have a high eccentricity object, you get high inclinations. I'm going to explain in a moment why this is the case. Yeah? So this is what happens here. Let me just show you how this looks. This is again the eccentricity first, so we're looking at the eccentricity. The planet is moving in. We have our bunch of planetesimals locally. Okay, so now here's a resonance. Some of these objects keep up, then they cross this Q line, then you get some scattering. Yeah, so once you're above this line, there's a chance that the orbit is planet crossing, you can get some scattering. And so you get these objects which have relatively high eccentricities. Yeah, and some of them really extremely high. Actually, some of them end up falling into the star if you do this. And now let's look at this from the side. So this is now, we look from the top again and from the side. So what you notice is as the planet moves in, first with the resonances, you see the eccentricities grow, but it stays still thin. But then the planet moves through and starts the scattering, and we get something which is thick. This is similar to the what Raymond calls the mini-Oort clouds. This is a similar effect what he has in his planet formation models. That you can get these optically thick or almost spherical structures of objects. These are still planetesimals, of course, but if you now start a collisional cascade, because we are moving into the debris disk phase in these transitional disks, then maybe you can produce a dust cloud which could be optically thin and which could be vertically extended. There are, of course, problems because if there's still gas in the disk, then the vertical extendedness of the dust component will not be long lasting. These particles will be stopped down and then settled again. So there are some trade-offs which we haven't really worked out yet, but we think that this is a pretty interesting idea. And if there is a planetary system evolving in these gaps of the transitional disks, then this is a process which could very well happen and produce these kind of dust clouds. So the end result of this one is that we actually get inclinations of up to 60 degrees, which would really do the job for us. Okay. Then I said the kind of planet which we want for this are Neptunes. Neptunes are the best. Because what you need in order to scatter into the high inclination is you need a planet which has an escape velocity which is comparable to the Kepler velocity at that location. It's kind of logical because you want to have a change in the velocity in the scattering which is similar to the local escape velocity in order to make a big change. And so planets like Neptunes are really good for this. And we know, of course, that there's lots of planets, at least in the lower mass stars. So maybe there's also Neptunes in the higher mass stars, and they would be able to do this job. Okay. The last thing which I want to say is a little bit about using disk properties in order to derive something about the mass of a planet. I'm a little bit running out of time, so I'm going to be very fast here because much of this stuff is, of course, known. So how do we determine masses of planets? Well, one is, of course, by Doppler method and inclination measurements. If we have both in a transiting planet, then we can directly determine the mass. This is clear for exoplanets. Then we can try to use the luminosity, and if we would have good models of planetary evolution with time, and if we would have an age of the objects, then we could also say something about the mass. This is basically one of the calculations which are used by Christoph Mordazzini in order to determine the luminosity as a function of time of the planet he's forming in his planet synthesis models. Another way to determine planet mass are, of course, planet-planet interactions, which result into timing variations, which you see in Kepler planets, so that's another way to do this. But a fourth way, which is, I think, extremely interesting, is planet-disk interactions. So you put a planet in a disk, it carves a gap, and maybe you can use this interaction in some way to determine the mass of the planet. So we have been thinking a little bit about it. So of course, planet-disk interaction, you all know how this works. You put a planet in a disk. There are torques from the planet which pushes the disk outwards. And there are torques from the disk which are due to the viscosity, which push disk material back inward, and the competition of the two decides of where this really is and what the shape of this outer disk is. And then the inner disk might deplete through accretion a little bit. So what we try to do with this, and this is also work by Gijs Mollers again, one of the PhD students, is he said, well, this inner wall of the disk set will have a shape, and maybe we can say something about the shape. So you can imagine that this disk could be extremely steep, or it could be more shallow, and that might depend on the viscosity and also on the mass of the planet. So what he did, he calculated models of a disk which has a very steep inner wall and then which has a more shallow one, so that the intensity which you get from there could be, the brightness could be very localized or could be broader and broader. And then he made a calculation of how this would look in interferometric observation. So this is a media observation predicted from this calculation where you have a vertical wall, which looks like this, and there's a lot of power in these oscillations which you still see there. And if you have a more extended wall, then you basically get a much quieter behavior here and a little bit different behavior in the baselines. And so Gijs tried to use interferometric observations which were collected by Olga Panic, together with also a couple of people here in Heidelberg, in order to say something about this. I can skip this slide. So if you look at the visibilities from MIDI for these different walls, you can try to fit them, and it's very clear that these more rounded off walls are much better fit to the visibilities which you see in this measurement here than to the more steep walls which you see by the red lines. And so Gijs then went ahead, and I mean, we don't really know much about hydrodynamics in Amsterdam, so we did it the easy way. We just took Fargo from the web and did some calculations for masses, for planets of different masses. So this would be a more low mass planet with a narrow gap. This would be a higher mass planet with a wider gap. And then with a, oh no, I'm sorry, so this is a surface density plot. And Gijs tried to make a parameter study for different values of the viscosity of the disk and for different values of the mass of the planet. And what he came up with is that he needs a relatively high velocity combined with a pretty high planet mass. So the planet mass which he came up with was that it's at least 20 Jupiter masses and maybe up to 80. And his conclusion was that right now we cannot really fully exclude this. So he looked at a couple of different possibilities on how to observe this planet. But it turns out that right now it's still quite possible that an object of this mass is in there. So that's one method when we think that this is a way to say something about the mass of the disk, even though it's a little bit degenerate with the viscosity. And the other method which we want to employ to measure this mass has to do with these dust traps, which case, of course, has been very important also in order to explain the theory of them. So these are a couple of observations from Van der Mare et al. And from Ohashi et al. In 2007, which show these rings at far infrared wavelengths, or even here this asymmetric structure, which is not only a radial but also an azimuthal dust trap observed by Van der Mare in this case. There's a couple more I don't need to show more. And there was this paper by Dom et al. In 2007, which was about the missing gaps with seeds. So the effect was that these far infrared observations kept showing up these rings, and that then the observations in scattered light didn't really show the gaps at that moment because the resolution was not quite good enough. And one explanation was here that there's a difference in the distribution of small and large grains which might be responsible for this. So we followed up on this, and what we actually used were the models which were calculated by Paola Pinilla and co-workers, putting a planet in the disk, looking at what the pressure gradient is doing in the disk, and then calculating the concentration of dust grains at a specific location. So these are the outcomes of these calculations, where you see that as a function of distance and then as a function of grain size, you see that the large grains are mostly located in this pressure bump, which you find actually quite some distance away from the location of the planet. And then the smaller grains are also present closer to the planet. So that's really why you would expect that there's a difference in scattered light, which sees the small grains, and in far infrared, which looks at the big grains. So what we then did is put this through instrument simulation. So we tried ALMA. We tried to use the sphere, because it was also our motivation for this. Will sphere be able to make a good contribution there? And also looked at VRT observations. So tried a couple of things and did instrument simulations for these kind of models. And this is one of the results for a couple of situations. So the first row is 1 Jupiter mass planet, then a 9 Jupiter mass planet, and a 15 Jupiter mass planet. And then when you see, for example, with sphere simple, what we think we will see, you actually see that in each case there is, so for the low mass planet, the gap is actually not really deep. There's still some material left. But if you increase the planet mass, the gap gets deeper and deeper. But actually the inner edge of the outer disk remains close to the planet, exactly what we saw from these earlier distributions. But of course, and if you go to ALMA and look in band 7, you see that this ring which you create there is moving away from the planet, because the location of the pressure bump is moving away from the planet. And the reason for this is the size distribution, as I said. So what comes out of these models from Paola Pineda is that indeed the millimeter grains are not present in the gap, and they peak far away from the gap, while the micrometer grains actually go through the gap, or at least to very close to the gap. So there's a clear difference there. And so the difference in the radius between where a scattered light image would show the gap and where the submillimeter wavelengths show the gap, that is a measure of the planet mass in some way. So we try to fit this for the calculation which we had. This is not yet a full parameter study, but it's a first step. So as a function of planet mass, we just calculated the wall location that we would see with sphere simple, and then we divided it by the wall location, or by the peak position of the ALMA ring. And when you see that there is really this correlation for this, so the different curves are for planets at different locations. This is a planet at 20 AU, at 40 AU, at 60 AU, and then you can calculate this ratio. And so you see that for the heavier planets, indeed, this ratio gets smaller and smaller. Again, there's probably an influence of the viscosity in the disk, which we haven't really tested out yet, but we believe that this is also a promising method for, in the end, providing constraints for the planet mass, just like the other things which I said earlier. And I would like to stop here with a couple of conclusions. So, one thing which I think cannot be said strongly enough, that I really believe that these Herbig stars are the key to understanding a lot of the things in the field of planet formation, because they are, and I think for a long time they will be, the best targets to do these observations. The group 1 SED sources seem to be all, or at least most of them, each of one, when we have looked carefully, turns out to be transitional. So I'm close to saying that they're probably all transitional, and in this way evolved objects with very likely a planetary system in them. Mineralogical features say something interesting about disk geometry, because their experience and strength also has to do with the disk geometry, but also says something about transport processes or about local heating events in one way or another. Still has to be investigated on how this exactly works. And then the interaction between the disk and the planet will give away the presence of planets, and it will allow to estimate masses. And now I'm done, and we'll happily take your questions.
Thank you, Carsten, for this very nice talk. Let's open the session for questions.
Is having a planet in the disk the only way to open a gap?
No, it's not the only way. I mean, there's other things that we could do by photo evaporation, for example, in principle. So there's still some discussion about it. But on the other hand, there are also these disks now which show embedded planets. So I think it's clear that there are companions and planets in these disks, and a couple of them they have been detected. And so I still think that this is most likely explanation. I think there are also some arguments why it's probably not photoevaporation. I forgot what the argument is. But,
Gas to dust ratio.
the gas to dust ratio. And what way does this work? Because I forgot how this argument goes.
In the case of photoevaporation, you would expect that there is no accretion going on, but there are transition disks which have quite normal accretion rates.
Yes, many of them actually have still some accretion. Yeah.
Actually, this is something I never really understood, because photoevaporation is just if you have hot gas, why can't part from hot gas accrete?
But that helps reduce the advantage.
So it's
Anyway, so I mean it's a fair question. We have to wait until we see these planets, but I think it's going to happen, and I'm very confident that this is most likely explanation.
further questions.
Actually, it's about the model you showed for the still basically swarm of black vessels, depending on what extent it is. Will this calculation actually done gas free or with gas?
They were done gas free, so the idea would be that these would be objects which don't really have too much trouble with working against. So these would be relatively big planetesimals, which are not slowed down by the gas so much. Or it would be in a phase where the gas is not so massive anymore.
Would you get a situation like sort of late heavy bombardment, heavy solid?
Well, that would be really early heavy bombardment. Because
Early heavy bombardment. But wouldn't you just see also that in sort of free-falling or evaporating bodies? I mean, I think you get a big, for instance,
Yes.
see this evaporating bodies coming into the
yes, there's actually, I mean, there's also this, there's this idea that these bodies in Beta Big are also being transported to Beta Big by a resonance mechanism. That is a different kind of resonance where the planet is actually sitting outside of a belt of planetesimals and then picks objects and pulls them into long eccentricities. That was an explanation in order to explain why most of these events, I think, are redshifted and not blue-shifted or the other way around. Yes, I mean, if there are planets in the system present at the same time, of course, there will be lots of impact on these planets as well. This would happen during the cleanup phase.
I actually have a comment and question. I mean, the comment is about subject one's protoplanet candidate.
Yes.
In Santiago, he actually, in a way, took it back because
So, okay, I wasn't
he
there.
pointed out that this emission is actually extended. We now found another object, and I think one has to be very careful also in the air reduction here, because the ADI is actually tweaked to point sources
Yes.
and can easily mimic standard emission of these disks. So I would be very careful to call these objects planets already. And Bas-Willer's object is actually not a planet, it's a low mass.
Yes, it's a more massive companion, that's right.
So I mean, you have a few cases where these objects are actually certain binary disks and not certain solid. But I still have a question concerning your argument with the 24 micron
Yes.
profile and the gap. I do not completely understand that. I do understand that if you go to flaring this and then if you check if this has a gap, then you can make a direct connection. And but I mean, why do I need the 24 micron profile to do that? So in other words, I can check my objects if I see flaring ACD, and if I see a gap, then I can make the connection.
Yeah, that's right, but I mean, this is just another way of figuring out that there's a gap. I mean,
Yeah, but why is the 24 micron profile telling you anything about a gap?
well, if you try to make a continuous disk model, then the 24 micron emission is dominated by material which is closer to the star. Yeah, because you have a lot of relatively warm material, much closer to the star, which produces a lot of 24 micron emission. And so this will be, it's just by chance. Our telescopes are 8 meters in size. These things are at 100 parsecs. So it works out the way that if you take a continuous disk model, that this that the main component of the emission will not be resolved at 24 micron. It will be a point source. And if you take away this material close to the star, then you have this wall, which actually gets a little bit superheated because it's irradiated directly. And then that location dominates the emission at 80 microns, at 24 microns. And if you measure the size of it, then you get a bigger size because you don't have the contribution of stuff which is closer to the star and which will dominate otherwise.
would practically work, so the Herbig stars, but it would not work for the Torres stars.
Exactly, would not work. So it's just a
Okay,
24 micron in this, for these stars at these distances with our telescopes is the sweet spot.
Oh, you need to be a telescope.
Yes, bigger telescopes are always a good thing.
Further questions? Actually, I have a question. It seems that in all these Herbig sources, group 1, group 2, all the cartoons, they have an outer N in their disk, or in other words, an outer disk, a huge gap, and then a little puff of smoke very close to the star. Is that for Herbig stars always the case, or maybe even also for these Howey stars, to kind of these traditional transition disks where there's nothing inside of the hole? Do they actually exist at all? Or?
I think that's a very good question, and I really want to know the answer of that question. But I cannot give you the answer. It turns out that I would think all, but at least most of these sources do have some warm material close to the star. I'm not sure how that is with the Howey stars. I'm not sure if this is the case as well. But for the Herbig stars, you always have a component of warm emission, which is typically at a temperature of something like 1500 Kelvin or even a bit more, which you see in the interferometric observations, and you also see it in the SEDs. So there's something there, and I actually don't really know what the mechanism is in order to produce this. It's weird.
You are first.
I have another question.
Or is this your point related to that? Or?
Maybe you said this when you were talking this. At a given young age, what is the fraction of Herbig stars that are in group 1 or group 2 or
Well, there's no clear correlation with age. So it's not that we can say that the younger Herbig stars are in fact mostly group 2, and the somewhat older Herbig stars are mostly group 1, because this would be great. This would be then proved by itself. One thing is that these age determinations are a little bit uncertain. That is one problem. And the other thing is that it really seems to be the case that the disk has a clock, and it's not the same clock as the star has. So it's actually very difficult to find quantities which correlate with age in at least the sample of Herbig stars which we have been looking at for a long time.
I just mean, are there roughly equal numbers of
Yeah, it's roughly equal numbers. Of the sample which we have, it's roughly equal numbers. It's also, I mean, imaging is also very interesting, because one of the reasons why we always talk of these group 1 sources as flaring is because there must be something like flaring going on, because in imaging of reflected light, you actually detect these disks, most of them, and to distances which are far greater than what the gap size is. So there's something there, and it turns out that the group 2 sources are really difficult to detect. So there's basically one or two detections in imaging. So there is also something in the outer disk which is different, which is puzzling, and that was, of course, one of the main reasons why the simple distinction, self-shadowed and flaring, looked like a really good model. And so maybe these group 1 sources still are flaring in the outer disk and are different in this way, but I think the more fundamental difference is that they have big gaps.
I wanted to come back to the dust traps, because I mean, you showed this different distribution of sizes.
Yes.
The days of planet.
This dust
I
traps.
certainly like the dust traps. And I think we should make the impression that we actually know the grain size in these traps. Because from an observation point of view, I mean, first the traps may actually be optically thick.
Yes.
Then, of course, you do not have a broad
We have no idea.
sizes, and there are no natural theta indexes in these systems. So I think at the moment, that's wonderful, great idea from an observation point of view, and we don't know.
Yeah.
So,
No, it's just, I mean, we picked an explanation for which we have a really good theory.
but I think it's important to realize that the observations do not constrain at the moment the grain size.
I think it's important to remark. It's only for modes, or the distributions which I showed.
Any concluding questions? No?
Over and out.
Over and out. So then let's thank Carsten again.